Good evening, everyone. Welcome to the fourth lecture of the 2019 keynote lecture series, Constructs, Digital Innovation in the Built Environment. My name is Eleni Papadamikoulaki and I'm a lecturer in Building Information Modeling and Management here at the Bartlett School of Construction and Project Management. Today we're very happy that we are welcoming Dr. Jennifer Schooling. And I'll give you some brief introduction about her profile and what she has been involved in. So Dr. Jennifer Schooling, OB, is Director of the Center for Smart Infrastructure and Construction, CSIC, at the University of Cambridge. CSIC is an innovation and knowledge center with a specific aim to transform infrastructures through smarter information. Jennifer is also the chair of a research strategy advisory group for the Center for Digital Build Britain, also at the University of Cambridge. Prior to joining Cambridge, Jennifer worked for Arup, the global engineer consultancy, for 6 years. There she led the firm's research business, delivering research strategy development to aid clients in targeting their investments to improve their productivity and competitiveness. During her work managing complex interdisciplinary research projects for clients, she developed a strong understanding of the demands placed on our infrastructure and the challenges of extending the design life of existing assets, of which more is being demanded all the time. Jennifer is also was also Arup's research relationships manager for the UK, working with staff and academics into maximizing the investments, the research investments. Jennifer has a PhD in material science from the University of Cambridge. So we will have a presentation from Jennifer on the role of sensing and data in infrastructure. This will last 30-35 minutes, and then we will have a Q&A session. So finally, please do tweet about this lecture, share your thoughts and the discussion using the hashtag digital construction. Thank you all very much for coming and enjoy the evening. Jennifer, the floor is yours.
As Eleni said, I'm here to talk to you about the role of sensing and data in transforming the future of infrastructure, which all sounds very grand. One of the reasons that this is a critical area to think about and embrace is that in a review, you can't really see this, but the important thing is what I'm going to point out in a second. In a review in, I think, 2015, McKinsey identified that the construction sector is one of the least digitized sectors in the economy. Globally, I think this was, not just in the UK. And if you look at that long list of sectors, construction appears just above agricultural and hunting. And I suspect that's probably doing agriculture and hunting a bit of a disservice, actually, because there's quite a lot of sensing now used in agriculture, and they perhaps are accelerating up the adoption curve a bit more quickly than we have been in our industry. And to fail to take advantage of the digital revolution is really to do ourselves and wider society something of a disservice, because not only does it affect productivity in terms of what we're building from new, but also it affects our productivity of our existing infrastructure. And so I'll talk a little bit about that over the course of the next 30 minutes or so. So I come from the Centre for Smart Infrastructure and Construction, so I always like to define what I mean by smart up front. And for me, really, smart infrastructure is a pretty simple concept. It's what you get when you use the digital to help you understand and manage the physical. I like to present things simply because I'm a bear of relatively small brain. And I think if we overcomplicate these concepts, then it makes them much harder to adopt. It's a simple concept. That's not to say that it is simple to deliver on, because obviously adopting digital technologies in an industry that's been around for several thousand years and in some of its practices hasn't evolved very much in that time for all sorts of good reasons, is a complicated and complex affair. Why do we bother with smart infrastructure? Well, it's all really there up in the top of the slide there. It's about generating better data and more information so that we can make better decisions more quickly and for better value for the benefit of the ultimate customer or user of the infrastructure. In the end, infrastructure is a public good. It's there to serve the city or the town or the wider built environment and to connect cities and towns and the wider built environment. So really we should always be thinking when we're thinking about infrastructure and indeed buildings, because buildings are a version of infrastructure, about who the ultimate users and ultimate customers are and how we can get most value out of our built assets for them. It's also a smart way of adding value to our existing assets. So this is a very, very, very basic graphic, and actually it kind of understates the case. If you think about the vertical axis on this arrow as being capital value, if you like, the vast majority of infrastructure that we have is already around us. And we add something like 0.5% by capital value to our infrastructure in the UK each year. And that's pretty comparable in developed economies. It's obviously rather different in developing and emerging economies, but in developed economies, that's pretty typical. And even in developing and emerging economies, actually, we've all, somewhere like China, which is building at a huge rate, already has a huge amount of existing infrastructure. Everything that was built last year is now existing infrastructure. So really, we need to think about enhancing the whole of our infrastructure portfolio. We do need to add sensing and digital capabilities and get better data from our new stuff, yes, absolutely, but we also must pay attention to our existing infrastructure. And I'll talk a little bit about that as we go along. If we do apply these advanced technologies to our existing infrastructure, then we're applying value across the whole of that infrastructure base. So something I like to talk about a lot is the value of data. And those of you who've heard me talk about this before will have heard me say this before. In the infrastructure and construction industries, we're really good at generating data, actually. We generate huge amounts of it very frequently. The problem is we are rubbish at curating it, absolutely rubbish. We generate vast quantities of data, and typically what we do is look at it once, see did it go over a threshold or not, and if it didn't, we go, phew, that's a relief, and if it did, we go, oh my goodness, time to panic. So we completely fail to learn what we can learn from the data that we're collecting. We invest a lot of money in collecting data. Nothing is free. Even digital data costs money to collect. But we then don't curate it in such a way that we can go back to it and learn from it. So, as an example, if Network Rail are collecting closure rate data on all of the points across the country, so the rail points across the country, as they do all the time, every day, what they're doing with that primarily is saying, is that set of points opening and closing at the rate we would expect? Because if it starts to do so very slowly, then probably the points have failed and we have to send someone running out to have a look at it. If they only look at, is it going too fast or too slow, then, or is it going too slow, then all they know is whether it's operating or not. On a cold day, the entire switchboard lights up red because all of the grease in the points gets cold and every single set of points goes slowly. So then suddenly they've no idea which points are at risk and which points aren't. Whereas if they'd been looking at the trend data and learning from that data as they went along, and perhaps looking back at last week's data and the month before's data, there would be less of a sense of panic in the control room on a cold day because actually they'd know which sets of points were most likely to be close to some kind of failure mode. That's a very, very simplistic example. It's true of many of the things that we do. So most of the time, what we tend to do in infrastructure and construction is collect data and look at it once. And then the biggest sin of all, we archive it somewhere that we can't get it back from, which is also costing us money and or carbon. So what we really need to get much better at is thinking about the data that we're generating and thinking what additional use and value could we be getting from this data, because it's an investment. And it's foolish of us to invest in something that we don't then extract the most value from. So we need to think about what else might we be able to learn from this data in the future, and therefore how should we manage it and structure it in such a way that we can go back to it and we can retrieve it from the place that we've archived it to, and we can then start to make sense of it using the very powerful modelling and analytics tools that are now emerging at such great pace, and that obviously organisations like Google and Amazon are leading in, but that are beginning to also infiltrate into our world. And that can then support decision making across the piece, help us to get better value out of our infrastructure, improved decisions leading to improved insights and leading to learning. So if you take one thing away from my presentation today, it's this. Data curation is crucial. You can now switch off if you wish to and go to sleep, as long as you remember this. That makes me happy. And this is the message that I think we need to keep repeating to people, because it's not well understood and it's not well adopted throughout industry. Obviously in academia, we've understood for a long time the value of data because it's what we use in our research, but even within academia, we're not terribly good at perhaps maintaining data over the long term so that we can go back and look at it. This is just a slide to show that there are lots of places you can get data from. In CSIC, we've used pretty much all of these, and there may well be some things that I've forgotten, but it's important really to realise that in the world of smart infrastructure, you can generate your data directly from your physical assets. So down in the bottom box there, we're talking about attached sensing systems. So, you know, sticking strain gauges on things will be something that many of you will be used to. Those are very important. They're very helpful. They can be very targeted. We've also looked at embedded sensing systems where perhaps we get the sensor and we embed it within concrete, or we kind of attach it more intimately to the structure. And that can yield very, very useful information, particularly with distributed systems. So if you've got an asset where you know you need to monitor it, but you don't yet know where the failure is going to occur, then having a distributed sensing system that can sense across the whole of the piece is really helpful. Sometimes they tend to have a slightly lower resolution, and therefore you might then, once you start to see problems, augment that with an attached system or another kind of sensing system. At the top there, we've got remote sensing, so looking at things like the use of satellite data. I've got a colleague who's working with various satellite organisations at the moment to understand how you can use satellite data, not just for the sort of bulk movements of the ground, which we're used to with, you know, monitoring, for example, the path of Crossrail through London, or back in the day, the Jubilee line, but actually looking at much smaller movements on bridges and starting to look for things like, can you detect a precursor to a bridge collapse? Which there was a fairly famous case a couple of years ago of a masonry bridge up in, I think it was in Yorkshire, that collapsed just before a bus driver was due to go over it with a school bus full of kids, and he kind of drove onto the bridge and thought, this doesn't feel right, and reversed back off it again, and the bridge went out from underneath them. Well, not from underneath, unfortunately, from in front of them. Now, that was a failure on a bridge that wasn't terribly interesting to monitor. You know, it wasn't some big iconic bridge like one of the Forth crossings. So you wouldn't necessarily have thrown lots of sensing at that. It happened to be a bridge, however, that had experienced a very heavy rainfall very recently, and although the weather on that particular day wasn't particularly dramatic, the foundations of the bridge had been undermined. It's called scour, for those of you that haven't heard of it before. So the bridge had experienced scour, which meant that it was potentially due to collapse at any point. As it happens, there is satellite data for that bridge, and my colleague has gone back and looked at the satellite data from before the event happened and has found that she can detect a few centimetres of drop in the bridge pier that collapsed from the days running up to the collapse. So if we can start to, for example, use sensing like that on some of these assets that are remote, in many other ways may not be terribly interesting or may not be of great concern, but actually for things like extreme weather events, we would want to look at them. And there's a real opportunity there to kind of take a portfolio approach to sensing, if you like. So not all sensing needs to be close by. Obviously, the other kinds of remote sensing are sort of drone-based surveys, laser scans, that kind of thing, which can be automated. And then the other data source that we found very interesting is social media data. So if you've got geolocated social media data, then you can start to understand, for example, what loading a piece of transport infrastructure has. Or if you're more in the sort of city planning arena, you can start to understand how people are using different kinds of space within a city at different points during the day, different days during the week, and that kind of thing. So not all data is actually physical data about the state of the infrastructure. Some data is about how we're using the infrastructure, and that is in many ways as important. And then, of course, that leads on, as I said, to the data analytics approaches and thinking about geospatial data analysis, but also the kinds of things that colleagues at the Alan Turing Institute are looking at. I'm sure you guys have collaborations there. I know that UCL is one of the founding partners, and we've got colleagues who are working with them as well to kind of start to unpick the vast quantities of data that you can start to generate and to find the needle in the data haystack, as I describe it, the thing that's actually going to give you some useful insights. So that's a bit of background. I'm now just going to talk a little bit about some policy context, if you like. I'm sure you've all read with great excitement 14 months ago the National Infrastructure Commission's report, Data for the Public Good. If you didn't, actually, I do recommend it to you. It's an interesting document. It also was backed up by 4 other interesting documents, one of which was written by Tom Dolan from UCL, looking at some of the sort of the background to how we use data and the opportunities that we might get from data. So data for the public good, that's the cover of the report there. And that's the list of the 4 technical papers, actually, which, as I say, are definitely worth looking at. And Tom's paper is the one about resilience of digitally connected infrastructure systems. What it identified was a couple of major challenges for our infrastructure based around our data. One is that we fail miserably to integrate data between infrastructure systems, but even within infrastructure systems and within, indeed, individual organisations. Now, that's for understandable reasons, because historically, we've divided things up into silos in order to be able to manage them and cope with them. But looking ahead, in this digitally integrated world, we ought to be undoing those silos again and working together, bringing the data back together. And then the other big issue that they identified was a failure to use data optimally to enable improved operation of our infrastructure systems. So this data-driven decision-making that I've been talking about this evening. And 2 things that they felt would be helpful in that was, firstly, to think about data as infrastructure. So I was talking earlier about the value of data. If we actually value the digital asset in the same way that we value the physical asset, suddenly it all starts to make sense. And if we think about, I'll talk a little bit later on about digital twins, the sort of digital representation of our asset as something that should come along with the physical representation, then it becomes much easier to sort of conceive of what the value might be and to describe that value. But we need new mechanisms to collate, manage and process the data, but it creates new opportunities, obviously, for society to better utilise our infrastructure assets. So if we combine our social media data and understand the extent to which people want to use London Bridge Station or Euston Square or what have you, then we can start to plan in a more informed way for future investments in that infrastructure, or to understand how we might get more out of it, load it to a greater extent, and smooth out some of the congestion situations that we experience. And then the other thing is that if we share our data properly, then we can improve efficiency, we can plan the infrastructure better, and we can get improved resilience. And actually, ultimately, sharing data can improve the opportunity for competition and innovation. There's a lot of sort of thinking in the commercial world that, well, I've generated the data, I've got the data, therefore, it must have value, so I must keep it. But actually, what's become clear in the last decade or so, for example, with Transport for London opening their data up so that other people can develop apps off the back of it, is that there's a huge amount of value in data being shared and data being collated and brought together. There are some challenges with it. So, for example, if I bring together data from 2 or 3 different sources, I can start perhaps to bring out pattern of life information. So we have to think about security when we share data. And we shouldn't just share all data with anybody. We should share data appropriately. But actually, there's a real opportunity for new and exciting innovations to occur off the back of data in ways that the people providing it couldn't possibly have thought of. So, enough about data for public good for now. What can we do with better data? So in CSIC, we divide the world up like this. We think about how data can inform the design process, the construction process, the management and operation of our existing assets, and then inform also how infrastructure serves the built environment, the city that it sits within. Because actually, the sort of the planning of infrastructure sort of comes at both the end and the beginning of the life cycle of infrastructure. But all of that underpinned in the CSIC world by the use and development of appropriate sensor systems, and then feeding the data from that into data-based decision-making processes so that you get data-driven decision-making, and ultimately demonstrating the value of these smart solutions. When I joined CSIC 6 years ago, I used to have fairly depressing conversations with industry where I would talk about, with great excitement, we should do all this instrumentation of stuff because then we'll understand it better, and the response would come back, well, why would I bother with that? Now the conversation has changed completely. It's very, very rare to get someone saying, well, why did I bother with that? Typically you get, yes, I understand, but how much does it cost? Which is also kind of the wrong question to ask, because it's not so much about what it will cost as to what value you will get from it in the long term. If it's going to cost you £1 million but save you £5 million, it's worth thinking about whether you can pull together the £1 million of funding. If it's going to cost you 100 but just give you back 20, don't even bother starting. So it's not so much about the cost, although obviously you have to be able to afford it. It's much more about the value that it will yield. So I'm just going to talk through some examples in each of those sort of 4 or 5 categories to give you an idea of some of the projects we've been doing. If you have projects that are like it, that we can also talk about to our industry partners, etc., then we'd love to hear from you about those as well, because the more we can present good value stories to industry, the more likely they are to adopt this stuff and stop releasing too much carbon in building new things that perhaps aren't so necessary and eking more out of the existing carbon investments that we've made, for example. So in terms of design, there's a real opportunity here to end up with better designs that use fewer resources and have better resilience. And this comes from really being able to validate our design models. We have a lot of very good consulting engineers. I used to work for Arup, full of incredibly bright people, using finite element models and other kinds of model. But these things all have lots of big safety factors designed into them, because up until very recently, we couldn't gather the data to calibrate those models. If we can now calibrate and validate our models, then we can start to see where the safety factors are excessive and pull back on them. Not too far, obviously, because we don't want things falling down, but to make sure that we're not expending resources and carbon unnecessarily. This can also help demonstrate cost savings and help us to design for whole life value. So there's a couple of projects I'll just briefly talk about. The one on the right-hand side of this slide is a project called Principal Tower, which is just down the road. I think it's in the City of London. And this is a project we got involved with because the engineers and contractors were concerned that they weren't really clear how good their models were in terms of monitoring or designing for the compression that a building experiences as it goes up. So when you're building very tall buildings, obviously, as the mass further up increases, you start to compress the lower floors, and this carries on all the way up the building. And the models are models. Models, by definition, are always wrong. That's the nature of them. And actually, calibrating this with standard kind of traditional measurement techniques is very difficult, because the standard thing you would use is something like a total station, but it's very difficult to get a sufficient angle on the building because it's within a built environment, so you're kind of trying to look through things, which isn't possible. And actually, by the time you get kind of sort of not even halfway up this building, the distances are too big, so you're not getting accurate enough measurements. So with this, what we actually did was embed fibre optics in various columns of the tower as it was erected, and monitor the compression of the tower as it was developed. So there's a very small graph there, but if anyone's interested, I can point you at papers and things about this, which sort of show that graph in more detail. But essentially what that shows is that, yes, you do see compression as the building goes up, but what you also see, if you can just about pick out these little things here, there are some quite significant excursions in the data based on hot days and cold days. And what it actually showed was that understanding the thermal behaviour of the building is at least as, if not more important, than understanding, if you like, the physical behaviour of the building based on the weight, the compression, because you've got, on very hot or very cold days, much bigger excursions. Now, this has implications, obviously, for how you design your facade. We're always fitting things out as we go, so understanding how much the building's compressing is very important, but also getting a better handle on some of these thermal excursions and thermal expansion and contraction is also important, particularly if, as we're striving for better energy efficiency, for example, we're trying to close up gaps. If you close them up too far, then you can get problems and things can start to crack. And also, the other entertaining thing is that if you get differential settlement, so if one side of your building happens to be longer on the day that you pour the concrete for the floor of the penthouse, and then it shrinks and the telly starts to slide across the floor of your incredibly expensive penthouse, or I know it's now, they're all attached to the walls now, aren't they? But if things start to roll around on the floor, then suddenly the value of your penthouse has gone down. So there's all sorts of reasons why understanding this thermal behaviour is really important. The other project that one of the other projects we've been involved in that explored a similar set of challenges was this one. This is the Liverpool Street Crossrail station cavern, and this is the passenger concourse in between the two running tunnels. This isn't dug with a tunnel boring machine, so it's been excavated, it's been sprayed with sprayed concrete, and then ultimately, you need to connect the passenger concourse to the running tunnels, otherwise it's just a very nice place for people to walk up and down, they can't get to the trains. So those two red blobs on either side is where the cross passages are going to be pushed through from the running tunnels into the ambulatory concourse, as it were. And in those areas, obviously, the tunnel lining is thickened, because that's going to experience some pretty interesting stresses and strains as the diggers punch through. And also it's then got to be able to take the additional load. Again, this was all modelled by bright engineers in a consultancy to understand what they thought the stresses and strains were going to do, and based on that, the tunnel lining was thickened throughout the length of that photograph there. And we were able to go in and instrument the cage in the area where the tunnel lining was being thickened, and then monitor it as they punched through the two cross passages. So the picture there is us instrumenting the cage before they put the additional spray concrete on. They then thickened the lining, and then these passages were punched through. And what we found was, as we expected, fortunately, that the strains that developed in the lining were actually much lower than the models were predicting, and they dissipated much closer to the mouth of the tunnel. So ultimately what that means is, for future projects, if one does some more measurements of this, because I would never do anything based on 1 point on a graph, but if we continue to do measurements like this, then we can, over time, reduce the amount of thickening, for example, which reduces the amount of concrete that's needed, which reduces both the carbon impact and the cost, but also sprayed concrete, for those of you that are familiar with it, it's a very nasty process. You know, it's not very safe. So the less of it you can do, the better from a health and safety perspective as well. So this is just a couple of examples of sort of using better data to improve design. In terms of construction then, we can do all sorts of fun stuff, especially using computer vision techniques. So there's the opportunity to create as-built BIM, which then has the opportunity to bring in quality assurance. Is what we built what we thought we were going to build? Is what the contractor did what he said he did, or what she said she did? Did the rebar go in the place that we thought it was going to? Did they put as much rebar in as they said they would? So digital verification and quality assurance is a real opportunity. There is some resistance to it in the industry, but actually there's currently the I3P, the Infrastructure Industry Innovation Programme, are looking at this in a project that's being led by the contractors, because they see the opportunities of really knowing exactly what we've built and having that as-built record. The other opportunity for that is then you can feed that as-built record into the management of the asset through its life, which I'll come on to later. You can monitor construction progress, so with your Google Glasses or HoloLens or whatever it is the next product will be, if you can put the model up in front of the construction site and georeference it, then you can start to say, well, okay, this part of the project is ahead, this part of the project is behind. You can also start to feed construction workers, or indeed asset managers in existing assets, information about what they should be doing, confirming that, yes, this is the right bit of the building to be working on, or this is the right bit of the infrastructure to be working on. That's the building that I now sit in, by the way. And then finally, you can do fun things like third-party asset monitoring. So this is a laser scan of St Mary Abchurch, which is down near Bank Station. Those of you who have the misfortune to have travelled through Bank Station know that it is historically a very congested station. So TfL are investing a huge amount of money in upgrading it. However, they're doing so bang in the middle of the City of London, where there's lots of heritage buildings, so, you know, slamming tunnels through underneath beautiful churches like Sir Christopher Wren's 400-year-old St Mary Abchurch brings with it some hazards in terms of preserving our architectural heritage. So we were fortunate enough to be able to get involved with this project and throw a lot of novel instrumentation at it, as well as the traditional instrumentation. So traditional instrumentation, again, for this, would have been monitoring points on the structure using total stations, so laser measurements. They can give you very accurate readouts of what's happening to that point, but they give you very little idea of what's happening in between. So for a complex masonry structure like this one that's been standing for 400 years, has had a few bombs dropped next to it, has had buildings built next to it, is already in a slightly distressed and you know, non-rectilinear state. Just being able to monitor a few points on it doesn't really cut the mustard. So we put fibre optics on it, we used laser scanning on it, and we delivered data to the contractors live so that they could calibrate that against the total stations, which obviously they're comfortable with, but we could also then look at how the structure was performing as a whole. The advantage of that was that we used that as the mitigation for the tunnelling process, rather than going in and trying to prop the building or pump underneath it with compensation grouting and that kind of thing. The reason that was a good thing was because actually with a very old structure, the best thing to do is nothing. The moment you start to pump compensation grouting in or try and prop the thing, you're interfering with a structure that stood quite happily for 400 years, thank you very much, and you may actually be doing it more harm than good. So we use the monitoring as the reassurance to the owner of the church and also to TfL that no damage was being done. And if we'd started to see movements that we weren't happy with, then the contractors could have modified what they were doing. As it was, they didn't need to, and they reckon we saved them about £1 million on avoiding unnecessary treatment of the building. So that was a really fun project, and if you go down to St Mary Ab Church and you squint at it appropriately, you can see the fibre optic monitoring, because we're still monitoring it now just to see whether it's settled any further now that the tunnels have been driven underneath it. So that brings us on then to structural health monitoring, which is now where we start to think about our existing asset base. So the stuff we've got around us, the 99.5% of our built infrastructure that's already here with us. And really the opportunity here of bringing digital tools to the table is that it helps us to understand and quantify asset condition and behaviour, assess deterioration rates, and then inform maintenance requirements. So again, I've got a little example here. This is a viaduct outside Leeds main line railway station. It's 150 years old. As you'd expect of a structure that's 150 years old, it's not in perfect condition. In fact, it's quite unhappy. It's so unhappy that when it rains and a train goes over it, the bridge cries because water seeps out of the cracks. So the route asset manager was a bit worried about this. The problem was it's 150 years old. They've no drawings for it. So they really don't know even what the original design intent was. They also know that it's had a number of things done to it over the last 150 years, but no real records as to when or why most of this happened. You can see some of the ties and things that have been put through, for example. The thing that they did to it most recently before we got involved, I don't know if you can see, but there's these sort of, in the middle of that sort of arch support there, there's some concrete that's filled in a relieving arch. Again, we've no idea why the designers put these relieving arches in. They seem to be part of the problem. So the engineer, without anything better to go on other than good engineering judgment, thought, well, I'll fill that in with concrete because surely that will help. It didn't. The cracks continue to grow even though they'd been mortared up. So at this point, they're scratching their heads and really don't know what to do with this bridge. But there's a lot of longitudinal cracking, there's water damage, there's rocking toe damage, which is fun, which is happening at the top of the pillars. So we came along with a whole range of monitoring techniques, including our favourite thing, fibre optics, but also computer vision, laser scanning, videogrammetry, and a very bright guy called Sinan Ajigosh, who's now a lecturer at Oxford, spent a lot of time scratching his head over the data. And at one point I came in and I saw him sort of sitting there like this. I said, are you all right, Sinan? He said, yes, I don't believe the data, but I know the data can't be wrong, therefore I can't quite figure out what's going on. And essentially what he discovered was it's behaving a bit like that, which obviously the route asset manager couldn't have divined without some better information. As the trains go over, essentially, they're sort of forcing the arches to rock backwards and forwards. The other neat thing that he discovered was that back in the day when this was built, it had quite diddy little trains going over it. Now, in the modern world, it's got much bigger trains going over it. And as it happens, the bogies of the trains that go over it now are exactly 2 arch widths apart in length. So as it goes over, it nicely forces alternate arches. So one of the things that came out of this was that Network Rail had dropped the speed limit over the bridge because they thought speed was the problem. And our monitoring was able to show that it wasn't speed that was the problem, it was just the fact of a train that was the problem. So if you're monitoring a structure like this and it's out somewhere where putting a speed limit in is going to cause problems on the line and congestion and so forth, actually they could have raised that speed limit. As it happens, it was sort of fairly close to the station, so they didn't need to. But the other thing that we're now doing is we put in different instrumentation that's focused on the cracks that we now know are of most concern, to monitor them and understand how fast they're growing, so that Network Rail can now start to think about what the right mitigation measures are and actually focus on the areas that are of most concern, rather than the things that look worrying, but actually the crack's been there for 50 years, it's not going anywhere, it's all fine. Which brings us on to another fun project that we had around giving an asset a health passport. So this is a much newer bridge. This is on the West Coast Main Line, where we had the opportunity to instrument a couple of new bridges as they went in. So some of my colleagues spent some very cold days up at the Laing O'Rourke facility just outside Sheffield, instrumenting concrete girders and things as they were being manufactured. And then they spent some slightly sunnier days instrumenting the bridge itself as it was being constructed. And the great thing about this is we now have data for this bridge throughout its construction, and now we're monitoring it during its asset life. There's a slide I didn't include, quite a knobby slide, that shows the train going over, and you can see all of the signals jumping around as the train comes over. We're monitoring that on an ongoing basis, and when we finally get the power to the place sorted out, we'll be monitoring it for every train that crosses it. The problem with that is you can generate terabytes of data in a day, so how on earth do we manage that? Which brings us to the data analytics. So we're actually collaborating with the Alan Turing Institute around this, and actually the Marsh Lane Bridge that I just showed you, to really understand how we can best use machine learning and statistical analysis techniques to pull out the data that's going to be most interesting. It's not a simple thing to do because they go away and they know about data, but they don't know about bridges, and they come up with all sorts of natty things and go, oh, how about this, how about that? And we go, yeah, that's because it's hot and the sun comes up and down, and so what we're seeing there is thermal expansion. Or actually, no, that's just a quirk of the instrumentation that we're using because it's running at a particular frequency. So there's some of they bring the potentially interesting bits to us, and then you still need the civil engineer to interpret, is that meaningful or not? What might it mean? But what it does, it enables us to churn through huge amounts of data in a way that we just can't with traditional sort of physics-based methods anymore, because there's just too much of it to get through. And that kind of thing can then be really useful when you come on to asset management, managing and operating infrastructure at a portfolio level as well as at a single asset level. So the work that's going on here is around stuff like condition monitoring and predictive maintenance, which builds out of what I was just talking about, but then also standing back and saying, okay, now that we have this monitoring capability and we can really understand our assets much better, we can do risk-based maintenance. So rather than saying, I must do this every year because that's what the manual tells me to do, which could either be very expensive because you're doing unnecessary maintenance, or oops-a-daisy, it fell down because we didn't do the maintenance often enough, you can now look at the actual risk to an asset. You can also start to think about that asset as part of a portfolio. So, for example, on a road network, if you have a bridge that's not particularly critical because you can divert traffic around it, or it doesn't get lots of traffic, so actually you can close half of the bridge for a while if you need to, then you might deprioritise that against, as Cambridgeshire County Council discovered in some work that we were doing with them, the bridge that is the only way in and out of a particular fenland community. In every other way, completely dull, but actually it's the only way in and out of this particular community. So they suddenly realised that actually we do need to pay more attention to that bridge. Although from an engineering perspective it's kind of boring, actually from a network perspective it's hugely important. Likewise, if you've got a bridge that has many of your public transport routes going over it, or is a major trunk road, you're going to prioritise that more highly than a small B road out in the middle of nowhere. So starting to bring in much more quantitative ways of assessing risk and then deciding where investments need to go, because actually we never have enough money to fix everything, to the best of its condition. So that's sort of some of these images up here. I'm just going to put up a couple more images that you won't be able to read, but this bottom one comes from some fun work that we did with TfL, looking at the jolly exciting topic of tunnel grouting. I know, doesn't sound very exciting, but what was interesting about that was getting them to think about value and what value meant to TfL. And where we went with that, and those of you that have done much in the realms of asset management will be familiar with things like employers' information requirements, asset information requirements, that kind of thing. You'll probably know about this, Eleni. That actually value isn't just about, is my bridge still standing up? Shock horror among a bunch of civil engineers. But it's about what matters to my stakeholders. So this was a value matrix that we created looking at the key stakeholders, which included the Mayor of London, the travelling public, the unions, et cetera, and thinking about what mattered to them. So the travelling public obviously want to get places on time, they want to feel like they're in a comfortable environment, the unions want their workers to be safe, the Mayor of London wants London to have a good image on the world stage, and actually you could connect all of that to different interventions in grouting. They had 3 kinds of grouting that they used. The cheapest was a factor of 1,000 cheaper than the most expensive, but through doing this exercise they got rid of the cheapest one because they realised it wasn't really bringing them value over the lifetime of what they were considering. They picked 20 years as a lifetime for a grouting activity and realised that actually the cheapest version wasn't going to bring them value, so they completely scotched it. And then the final bit of work we've done here is around future-proofing and I'm not going to go into it in detail because I'm running out of time, but thinking about actually how do we understand what the future challenges that our infrastructure is going to face are, and decide which ones of those we should prioritise from a future-proofing perspective. Because again, budgets are limited, you can never future-proof against every eventuality. So what are the issues, how important are they to a particular asset or even component of my infrastructure assets, and how future-proof is my current design or my current asset. So that then helps you pick out where some of the gaps are. So you can see on the spider diagram some places where the aspirational line in red is quite close to the blue line, which is today, and some places where the gaps are bigger. And actually give, again, a sort of quantitative way of speaking with evidence about actually where do we need to focus our attention. Which brings us to cities, where we can do all sorts of fun stuff at a district and city scale, and using, again, quite a lot of the time social media data for some of this, but also looking at energy assessments, how much energy is a particular district using, what's the potential there for perhaps to use ground heating and cooling to provide for the energy needs of a district, etc. So that sort of hangs together in our world. These are the kinds of projects we've been doing. And we talk about land use planning and transport planning, which are topics that obviously you're very familiar with in the Bartlett. We've also started to look at the three-dimensional city. So we've done some fun stuff with the British Geological Survey, understanding how the ground responds to things, looking at the Royal Borough of Kensington and Chelsea, as it happened, and bringing together BGS's data about the geological condition of the ground and the water table and flow rates within that, alongside information about who's building big new basements, to put their home cinemas in and that kind of thing, and actually the impact that that's going to have on the ability of the ground to both soak up heat and provide cooling, but also, is that going to, how sustainable is that? Because the ground is a finite resource. We're also, interestingly, starting to think about using that same approach for transmission of vibration, because London Underground have been finding that train lines that have been knocking around for 100 years and no one's ever complained before about the vibrations, someone builds a new basement and suddenly they get complaints from another building that's been there for 50 years, say, because the vibrations are starting to reflect. So this sort of planning in 3 dimensions is a really interesting topic, and something that we've not really done. I mean, we've done planning above the ground in 3 dimensions to some extent, make sure that you're not going to get in the way of flight paths and that kind of thing, or the view of St Paul's. But the underground planning and understanding what the resource of that ground is something that's a sort of emerging area for attention. And I'm just going to spend a couple of seconds on this project, Digital Cities for Change, because what we've started to do, and this is a project funded by the O. Bartlett Foundation, is think about, well, all this tech's great, but smart city projects and programs have tended not to flourish. There have been a lot of demonstrators in the smart city world, but they almost never scale up. And why is that? And a review of the literature and some work that the Future Cities Catapult did was very instrumental in this, revealed that one of the problems with it is that they tend to be technology-driven rather than need-driven. And actually, when you're applying something at the scale of a city, a smart city intervention really needs to be designed to meet the higher level policy goals of the city and the higher level needs of the city. So it's completely understandable. Again, in the early days of any technology, people find a technology and think, this is brilliant, what fun, what can we use it for? But actually, in the context of city scale challenges, that doesn't scale well to wider scale adoption. So we've been doing a project, as I say, funded by the O. Bartlett Foundation, looking at both governance through technology, but governance of technology as well, and bringing some of the sort of more social science and political science disciplines into this to start to grapple with actually what does it mean. We're talking about digital twins in here because we're doing a project with Cambridge City Council around a digital twin for them. But what opportunities does digitalisation bring? And can the digital tools that we might have at our disposal, some of which might be digital twins, act as what are called boundary objects in the literature, effectively mediation tools to enable me in housing to get together with you in planning, to get together with you in energy resources and understand, and then the person who's responsible for air quality and someone else is responsible for transport, and understand how all those things fit together and actually bring the data and information that we have together across our silos so that we can make joined up decisions. Because it's very difficult the way we currently structure our governance systems to do that at the moment. And the bigger challenge will be not just sort of imposing new digital technologies on current governance systems, but actually thinking about how should we change what we do to get the best out of these digital technologies, and should we be approaching things in a slightly different way. nearly done. I've got a couple more minutes to talk about. Just a bit of information for those of you that haven't come across it. So back to data for the public good. It recommended 3 things: a national digital twin, a digital framework to enable data to be shared securely, and a digital framework task group to coordinate all of this. And that they suggested that the Centre for Digital Built Britain facilitate all of this, which brings us to the question of what's a digital built Britain. There's a lot I could say about this. There's entire slide decks on it, but just very briefly, what I will say is it's about sort of slightly different words to what I was showing before, but essentially bringing together the design, the build, the operation, and the integration of our built environment, and understanding from the beginning what information is needed. So in terms of how we want to operate our infrastructure, that bottom right-hand quadrant, what do we want to get out of it? How do we want to connect the different kinds of services together, both in reality and conceptually? What information do we need? How do we get the right feedback loops in place? And how do we then use that to enable better whole life value from our infrastructure? So that's sort of the mission that CDBB is espousing and has some responsibility for on behalf of everybody else, thanks to the National Infrastructure Commission. And just recently, the Digital Framework Task Group brought out this document, the Gemini Principles, which if you're getting excited about digital twins and digital information frameworks and all that kind of thing, I commend to you. Essentially, this is a set of principles about digital twins and what they should be for, but it's also a set of principles about an information management framework, which really will underpin this. So essentially, very much in summary, it talks about there being 3 key components to a digital twin, particularly for infrastructure, but I think this is true of everything. It must have clear purpose, and that purpose must be for the public good, particularly if it's around infrastructure. It must enable value creation and performance improvement, and that value creation could be social value, it could be economic value, it could be better profits for the developing company, it could be all kinds of value, but it should enable value creation of some sort, and it must provide insight. So that's the purpose piece. Very importantly, it must be trustworthy. So it must enable secure sharing of data between appropriate parties. It must be as open as possible, without saying that all data needs to be open to everybody. And it must be built on data of an appropriate quality. Doesn't mean all the data has to be fabulous, but it does mean you need to know what quality that data is. So metadata about data is really important. And then finally, it must work, obviously. Part of that is when the National Infrastructure Commission first talked about a national digital twin, various people, including me, threw up their hands in horror, thinking about things like in the UK, the disaster that was the National Health Service's attempt at a national digital system. It very quickly became clear that it would not be a single national thing. It's going to be a federated set of things that operate at different scales. So we may have some twins that are at the national scale, but they won't be anything like as detailed as the twin of this building that the facilities manager of this building needs. This building might share some data with a national twin or a district level twin, but it won't be all of the data about, where these pipe runs are, etc. It must be curated, coming back to my favourite word, and it must, crucially, must be able to evolve, because we don't know where this technology is going. 10, 12 years ago, none of us had smartphones. Who can live without them now? My mother, but she's the only person in the world, I think. So, we can't imagine where technology will be even in 10 years' time. So we must, if we're creating these essentially data resources, which is what this is about, they must be able to evolve and interoperate with future technologies that we haven't imagined. So I think that is the end of my talk. The value of data and data curation is what I want you to take away. Thank you very much. Yeah. Not knowing that data is being used for that purpose. Just a few words. So I think it would be fair to say that we're in the foothills of this, of exploring this. The piece of legislation that came out last year, it's late in the evening, I can't remember what it's called. You'll know the name of it. That means that people can't keep our data. GDPR, that's the lad. So GDPR made us all throw up our hands in horror, obviously, but actually, there's a lot of good stuff in GDPR, which is true of curating any data. And the good practices that GDPR will cause us to embrace are actually applicable to everything that we do. The issue around inadvertent or advertent monitoring of people is a really tricky one. I talked about the old church that we've been monitoring. We were also monitoring Mansion House using a visual technology that showed a massive leap when the lighting conditions changed. And you can kind of account for that because, yeah, you know it's going to happen. But what was interesting was the data showed this sort of, you expect the leap during the day as the sun's moving around the windows and things, but if you get a leap at 7 or 8 in the evening, you know that someone's in the building. Okay, that's fine. If you get a leap at 7 or 8 in the evening, 3 days before Theresa May is due to turn up and make her Mansion House address, you know she's probably in there practicing. Now that could be a security risk, and it's all coming from a camera that's there to monitor the structure because there's a tunnel being driven underneath it. So the challenges around security and ethics and that kind of thing is something we're very aware of. I wouldn't say we know quite how to deal with them yet. We've got, one of the fortunate things we have in CDBB is that we have someone from CPNI sort of seconded to work with us and make sure that we are aware of this and that all the projects that we get involved in with researchers and practitioners around the country from other institutions are also aware of this. So there's an ECR fellow here doing a CDBB project who will have had her security briefing. But it's a tricky one because you can learn all sorts of things from data that people didn't think about when they gave you the data. That wasn't really an answer, was it? Sorry.
Any other questions? Yes.
Hi, Kirsty Woodward, new Chair and Senior Lecturer there. How do you convince people to actually use smart infrastructure in their construction? One example was recently I was fortunate enough to visit Bank Capacity Upgrade, which was actually going underneath some quite important buildings in the centre of London. And they were doing some transferring structures underground where they were actually taking the bottom ends of the piles and transferring them around the tunnels. And my instant question was, have you got fibre optics in there? Because it would be great to actually see whether the loads are actually coming down that far, and then whether they're actually being transferred. And they said that they've been advised actually not to do anything like that, not to release any information. And unfortunately, I was only there when the last one was installed.
So there is at least one building that did have fibre optics in it, precisely because of that.
Yeah.
I can't say anything other than that, but there's at least one building. And the reason they did it was to make sure that so I think it was a request of the building owner, because they wanted to know that if ever they wanted to add more floors to the building, that the foundations would be able to take it. There is a challenge, though, of getting people to adopt smart infrastructure solutions because we have a culture of litigation in our industry. So people don't necessarily want to know that stuff isn't working. I had some interesting conversations with an organisation that is building a facility that they would worry about the security of, and in which there is a huge amount of steel, which means that fundamentally you can't pour the concrete past it. And we all know this. So my suggestion was, well, why don't we do some tests where we reduce the amount of steel, or we can do some tests with the amount of steel that you specify and demonstrate that the concrete's rubbish, and then do some tests with a reduced amount of steel and demonstrate that you get at least as good a structure. And the answer was, yeah, but if we did that, we'd know how bad all our existing structures were, and we don't want to know that. But I think that's going to change. And I think things like the digital verification kinds of project that I was mentioning that the I3P group are looking at will start to make that culture change. I think the other reason it will change, frankly, is the thing that's worrying me a lot at the moment around climate change and climate change mitigation. We've got 10 years till 2030 when IPCC says if we haven't sorted it by then we may find we can't. We can't just keep pouring more concrete just to make ourselves feel safe. We have to start thinking about risk more systemically. And yes, there's a risk to health and safety, and we need to make sure our structures will stand up, but we also need to make sure that they're not doing other kinds of harm. And I think actually carbon emissions is a kind of harm. So I think thinking is changing. Whether it's changing fast enough, I don't know. But that is a challenge. You have to find the person who cares about the answer, basically.
Hi there, George Harler from Mace. Probably building actually. It's more around, I suppose, the who and the where. Does that thinking need to change within the industry? Is it the designers? Is it the clients? Is it the consultants, the contractors? Is it everybody?
So the short and rather glib answer is it's everybody. And I think we've all got a role to play. So the designers and contractors who are kind of at the leading edge, we've got a lot of brilliant people that we work with from a range of consultants and contractors doing demonstration projects and actually then adopting stuff into practice. You know, we're the people that really understand the engineering nuts and bolts, as it were. So we're the people that should be explaining what that can bring. There's very much a kind of feeling in the industry of, oh, well, we need to wait for the client to specify it. But the client doesn't necessarily know what to specify. So we have to lead them to that. But obviously, ultimately, we have an industry that's extremely responsive to what the client wants. And so if the client asks for it, the industry will jump, which is partly an answer to your question earlier. You know, if the client says it will happen, then it will happen. So we need to work at both ends of that spectrum, I think. And we all, as engineers, have some of the responsibility to do that. So it doesn't matter whether you're the project director or, you know, some fresh new graduate just arrived in a company. We can all raise our voices to say, actually, this is an important thing to be doing. We need to better understand our existing infrastructure, eke more out of it, invest our carbon wisely, invest our money wisely. So I think we've all got a role to play in sort of selling the opportunities that better data brings. And that better data can be all kinds of stuff, not just the sorts of things that I've talked about today, which have been very wide-ranging, but, you know, any data that you like. Kristen Henson from the KHL Sustainability talks about, can we even, you know, order of magnitude estimate, how much steel and concrete is in a structure? Can we share that with each other? So we can know if we're getting better or worse. It doesn't have to be minute details of microstrain. Obviously, that's fun, but...
One of the issues appears to be the whistling.
One of us is singing. Your magic.
One of the issues seems to be that less so in infrastructure, but certainly in building, there's a bit of a culture of build it and walk away.
Yes.
And the whole idea of a life cycle and had its own problems. And there's also, with the Internet of Things, there are maintenance issues. And if the client moves on, who's going to keep on maintaining the information?
Yeah, so this business about maintenance of information is crucial, and it's, as you say, in buildings you have the situation that people, there's a bit of a tendency to build it and move on. Ultimately, I think regulation will catch up with those people. So the people, we kind of try and work with the early adopters and the early followers, as it were, in the work that we do. The people that can get value, can see that they can get value out of it now. So some of the bigger developers who build to rent, and you know, the insurance companies and pension companies increasingly are investing in property to get an income out of it rather than just build it, flog it and run off. They're starting to see that there's a real opportunity with understanding data about the systems. I've talked mainly about structural data, but actually there's all the performance data around, you know, how the heating and cooling systems work and all that sort of thing. So in terms of the value, I think the people who lead the thinking will get there in buildings in the same way that they're getting there in infrastructure, and then everyone else eventually will be legislated into it, so that's fine. For the stuff that matters. We don't all need information about everything. We need appropriate information about the stuff that matters. The challenge about the life cycle of information, though, is a really tricky one, and part of the work that the Digital Framework Task Group that I mentioned earlier is doing around the information management framework, there's a lot of acronyms in my life, we'll need to deal with this business about how we hand data on, not just between sort of phases of a construction project, but phases of the life of an asset. And within that, you get a lot of organisational changes, you get a lot of technology changes. So you really do need a strategy for future-proofing the information. Because there'll be information that's generated early in the life of an asset that's important later. You know, that 150-year-old bridge I showed you, if only we had a drawing and some notion as to why they put those relieving arches in, for example, you know, we'd be a long way ahead. If we had a few records about what some of those maintenance interventions were, it would be great. But they've been lost over the course of time. The good thing about the old technology is it was mainly written down on paper, so the only technology we needed in order to read a drawing from 150 years ago is our eyeballs, whereas the kind of data we're generating today is digital, and I no longer have a digital copy of my PhD because it was on a 3.5-inch floppy disk, which you can tell by the name 3.5-inch. It's pretty old school and is now in a bin somewhere. So we mustn't bequeath that legacy of lack of information to future generations of engineers. That would be a crime. So we must think about that as we go along. I think BIM and the digital twin will help with that. I'm optimistic, but only if we're proactive about it.
So you touched upon the extreme end of how we manage the old assets and how we are looking at the new assets. So the border provisions which we have for modeling new assets, say the board for design, for C. So how do you look at those digital twins and monitoring those digital twins and updating the codes and looking at, are we really using more steam? And because most of the designs are just following it should be compliant, but we really don't know it's what we needed, as you touched upon risk-based maintenance. So in that view, how do you look at the design process?
Sort of risk-based design.
Yeah.
So I think, again, I think there is a culture change coming. The problem with codes is they're intended to be the minimum and they become the maximum, and the easy and financially expedient, brackets, lazy thing to do is just build to the code. That's all fine. And if you're doing pretty basic structures, why would you do anything else? But we should think about revising the codes because of resource limitations and so forth. I think post-Grenfell, there will be a change of attitude in terms of the sort of, because one of the challenges and one of the reasons that we tend to design to the code is you lose control of your part of the design process and it gets passed on to someone else. If you go back and read the technical reports into Grenfell, the BBC for a while had a link up, I don't know if they still would have, on Barbara Lane's report into the progression of the fire at Grenfell and the design and construction issues that caused the conflagration. And pretty much everything that could have been done wrong was done wrong. And that wasn't because people intentionally set out to make a fire trap. It was because there was no kind of overarching vision as to what role each component and each task had in providing that fire protection. So I think coming out of that and the reviews that are going on to the regulations and so forth, there will be a change in attitude. I mean, if you read Dame Hackett's report, it holds up a fairly unpleasant mirror to our industry and says, well, look, folks, you've got to grow up and start to take responsibility. And I think that will then bleed through into modifying codes, modifying designs, and taking this sort of more systemic view of what we're doing, which is the only way, really, to change it. But we've all got a role to play in that. Try and stay motivated.
Such that when a building is built, is there some control framework, some standard to ensure that probably such sensing technology or mechanism is part of the added somehow to that building, such that if there are any issues, it could send of information to people who can act on time before it becomes a disaster. And also, especially in underdeveloped countries or collapse at a critical time when there's a lot of people using. So I was just thinking, if there had been some sort of technology of this nature available, or some control standards to regulate the practices, not just for the government to, or for just people, a certain group of people to just look at iconic figure, I think infrastructures or buildings across, maybe anywhere in the city. How can this now be made available to the people in general and mainstream?
That's a very good question. I'll deal with it in two parts. There's the bit about sort of structural integrity, and there's the bit about, I would say, comfort. So to think about structural integrity and quality of construction and that sort of thing, that is definitely coming. I think it will be probably trialled in the more developed economies where we've got the money to figure it out how to do it. But the great thing about a lot of this is it's based on digital camera technology. And actually we're getting to the point where, my phone has a much better camera in it than any camera I ever bought before, back in the day. So actually, and the thing about construction sites is they're muddy, difficult places to work, so it has to be simple to do. So I think it will ultimately be very adoptable by people in, other circumstances where perhaps there isn't the money available to help develop the kit, but actually using it will be something that becomes, it should be so simple to use that it doesn't matter where in the world you are, you can still use it. Obviously, whether or not people choose to implement it is then a matter of governance, and I think that will be up to the local government regulation. Something else that's coming out of the Hackett inquiry and the sort of follow-up to that, though, is around digital compliance with regulations. And I know also that a lot of the standards institutes around the world are thinking about digitally readable standards so that you can demonstrate digital compliance. So the more we move to that sort of thing, because at the moment, even in this country, the poor old buildings inspector can't go around and inspect everything. They inspect the important bits of some things. Is there a steel there? Yeah, okay, great, I'll trust that there's a steel somewhere else. But actually, the more we move towards this ability to demonstrate compliance digitally, then I think we will get better quality coming out of it. And there will be an attitude and a culture change. But it will need to be enforced. The business about what people can expect from buildings in terms of, say, comfort and IoT sensors to tell me whether this room is too hot or too cold, that's coming already. So I've got colleagues working on that in Cambridge. I'm pretty sure there are people at Imperial working on it and various other places looking at actually how we use digital twin technology to help with what is essentially facilities management and asset management, so that we can automatically raise repair orders or at least investigation orders through the system so that the asset manager can know, because most in universities are a classic example. You've got hundreds of buildings and they're all different ages and they've got all kinds of different kit in them and all kinds of different uses, from lecture rooms to, I don't know, big chemical engineering plants and things. And it's quite hard to keep track of that. Now there are digital systems in place, but most of them don't talk to each other currently. So you've got one system monitoring one set of things, another system monitoring another set of things, probably nothing monitoring the state of this room until one of us complains to asset management that it's too hot, too cold, whatever. So they're already starting to look at how we draw all this data together. So I think that will be around in 5 to 10 years. We'll have pretty good systems for that kind of thing. The digital regulation piece, it's harder to know because that does involve some fairly sophisticated compliance systems, I think. But it's coming. Definitely.